Illumination is an important subject in graphics. Every objects get illuminated by a source of light. In this case, I have different objects kept on this table. Illumination depends on the play of light. There is a light source, maybe the sunlight or an artificial light, which illuminates the object. The light scatters from the surface of the object and reaches the camera, which records the intensity of light and scattering. Now this object looks blue, this object looks transparent, this is metallic, while this Rubik's Cube has different colors, red, green, blue, orange. These colors are intrinsic property of these objects. The illumination, the ambient illumination that you see is coming from all directions. It's the same for all objects. So there is two components to this. One component is the ambient illumination. The other component is the intrinsic property of these objects. And here I have an object which is emitting light by itself. There is an LED which is illuminating this object, and it is a source of light. So I may have other objects which are not sources of light, where I have an ambient, but now here this is a light source which is hitting this object, and due to this light source and other light sources, there is a directional light which is coming and hitting these objects. It is not an ambient light source, and due to which there is a shading which occurs. You see a shadow of these objects. As you see here, the front surface is of a different intensity. Each surface looks like it is in a different intensity. You have now it has to be seen, how do I create this model? Of course, I can create a model out of physical relationships, scattering laws, and these sort of thing has been done earlier by me for doing cometry studies, where I study the scattering of light from a comet and compute and try to find out what are the scattering properties or the dust properties of a comet, and through which we create a model of the comet. So basically, the scattering laws work on physics, and you run a physics model to derive your scattering laws and to see, so that you could explain the reflected light which reaches the camera. However, this computation is an extremely tedious computation or extremely costly computation, requires a lot of computational time and computational power. So we will try to devise a model, an empirical model of illumination, which can try and simulate the actual reality. But with the advent of more and more powerful computers, slowly we are returning back to the actual modeling of the scattering through models of physics. But today we are going to construct an empirical model or a hack which is going to simulate. It is not physically correct, but it is going to simulate. Audience looking at the graphics will feel that it is an actual scene or an actual
Illumination is an important section of graphics and visual computing. In this section, we will learn how to color a pixel, a graphics, and shade a graphics so that the graphics looks a three-dimensional object. We will also see the play of light and shadow, which makes the graphics look like real life. To give you an example, here are two pictures. The left one is without lighting or just rasterization. It looks like a silhouette or a cutout of different geometric shapes, three-dimensional geometric shapes. While the figure on the right depicts these geometric shape in 3 dimension. This is possible because of the lighting. You see the shadows, shades, and this peculiar lighting, that is the bright spot that you see on these objects, from which I can make a guess that these objects are pretty well polished and it is reflecting a lot of light in these regions where there is a peculiar point which is there. Basically, this is the region where the mirror reflection, the laws of mirror reflections hold good. So, illumination. How do we compute radiance for a simple ray? All objects in my graphics is illuminated by some light source. In this case, it is the sunlight which falls on different objects, and these objects scatter the light, and the light that enters my eye is through which I see these objects in the world. So basically, the scattered light or the reflected light from different objects reaching my eyes. It is possible that some objects, the light is refracted through the objects, reflected through the objects, or scattered through the objects. We see it only when the ray reaches our eyes or the camera. Solve the right problem. We somewhat understand the perception of light, color. We need a solution to represent and generate light, color using computers. We need to understand to interplay of light and objects. Here is a sphere which is there in the St. Peter's Cathedral at Vatican, where due to the shape of the sphere, you see a practically close to 180 degrees view. This is something like a fish-eyed lens or gives you an extremely ultra wide angle lens. So through just imaging the reflection through this on over this sphere, you can get the picture of the whole cathedral. However, there is a distortion in the picture, and this distortion depends on the shape from where the light is reflecting. In this case, it is a sphere. Here is an object placed on a checkered board or a chessboard. Now there is an optical illusion that may take place. The intrinsic property of the chessboard is that it has got white and black squares. Now, are the white squares and the black squares of the same intensity or the same color? They don't look like. That is because they are contrasted with white and black squares. But what you see is that an optical illusion can be created by looking at a black square in light and a white square in shadow. And both could actually be of the same color. Let us concentrate on these two squares. The square A, which is a black square, which is illuminated, while the square B is a white square which is in a shadow. If I cover the other squares, we will see that both A and B are practically of the same shade. A white looks similar to the black. That is because of the illumination. The intrinsic properties also of the object changes due to the illumination. We also see the similar effect on this cylinder which has been kept, where you see the direction which is facing the light has a pretty light green, while the region which is in the shadow or the opposite region is practically black. So, what you have is a gradation of intensity variation, and this gradation is due to the shadow effect and the shading that occurs due to the light which is scattering from it. The intrinsic property of the cylinder is that it is of a green color, but here there is a variance of color just due to the illumination or how the object is being illuminated. Lighting. If we are attempting to create a realistic image, we need to simulate the lighting of the surface in the scene. Fundamentally, simulations of physics and optics. And this is possible. In fact, it's done in a lot of physical problems where you try to understand the property of the material through the scattered radiation. Basically, the refractive index of the material are the intrinsic property of the material through which the light reflects or refracts, and this intrinsic property reaches our eyes through the refracted or reflected beams from these objects. So, a proper physics calculation using Mies scattering or above or more complicated codes can be used to determine this illumination, but it makes it extremely complicated and difficult to compute. As you see, we used a lot of approximations, a perceptual based hacks to do this simulations fast enough, because this illumination or the graphics needs to be colored at real time so that I could play games in real times, and it doesn't hang the system. It should be light and computationally light and fast to do these coloring. Definitions: illumination, the transport of energy from light source to the surface and points. Note: includes direct and indirect illumination. What I mean by direct illumination is the light falling directly from it or emitting. For instance, in this image, I see this white portion is a source of light, and this is a direct source of light. Or here you have the direct sunlight hitting the walls, and you see this bright spot. But the other walls that you see is basically this light which has scattered across the room, and we don't know from which direction this light is hitting these walls, but it is illuminating these walls. After maybe multiple scattering, this light reaches the camera and this photograph can be taken. Similar, we see in this effect, we see this beautiful scene that we have already visited before, and this is graphically generating the light and shadow and the reflections through which the room looks extremely clean. The floors are very mirror like and polished. the walls are extremely well polished, and so on. We continue with the definition: lighting, the process of computing the illumination intensity, that is, the outgoing light, at a particular 3D point, usually on a surface. Shading, the process of assigning color to pixels. Illumination model falls into two categories: empirical, simple formulation that approximate the observed phenomenon derived from experiments; physically based, models based on the actual physics of light interacting with matter, and this is extremely complicated and requires a lot of knowledge of physics. We mostly use the empirical model in interactive graphics for simplicity and to reduce on the computational power. But increasingly realistic graphics are using physically based model with the coming of more high performance computing with extremely efficient GPU cards. This is now becoming a reality to generate these physics models in real time. Components of illumination. There are two components of illumination. One is the light source, and the second is the surface properties. As we had seen earlier in the chessboard, the surface property of the chessboard was one was a black square and the other was a white square. But due to the property of the light source, in one case it was illuminating it directly, in the other case it was a shadow, and because of the shadow and being the black square being illuminated and the white square being in shadow, both the white and black, which were the surface property of the chessboard, looked of the same color. Lighting source or emitters. What we need to understand from these emitters, or what we have, is spectrum of emittance. That is it a totally a white light, the color of the light which is emitting from these sources? We need to know the geometric attribute, position, direction, shape. It is possible that the illuminating source or the light source is not a point source but has a physical dimension, and because of the physical dimension there is a property of shadow which is created where you have an ambra and a penumbra. This ambra and penumbra we will visit later on happens when your source is not a point source but an extended source, and due to the extended source there are different ways the shadow falls. There's a partial occlusion and a full occlusion of the objects on other objects. Directional attenuation, that is the light traveling from the light source to the object, gets attenuated. This happens when there is a lot of mist or dust in the air or some other material, or we are talking about large distances through which light is traveling, like the light from the sun. There is sufficient amount of attenuation. And of course, we can also discuss about polarization, light scattered or reflected through different objects may as well polarize, or pass through a polarizing filter may also reach the objects in a polarized manner. We continue with the components of illumination, and we have seen that there are two components of illumination: light source and surface property. Let us now see the surface properties. The reflectance spectrum, color of the surface, is important. Is that how the light is reflecting? It is possible that a white light touches different objects. Like for instance, I have got this leaves where there is light which is hitting these leaves, and the scattered light is in green color because the intrinsic property of the surface or of the leaf is green. So other rays of light from the white source gets absorbed, while the green portion of the spectrum is reflected towards the camera. The geometric attributes, position, orientation, microstructures, are also important related to the surface properties, because it depends on how the light is incident on the object. Depending on the incident beam, the angle to the normal to the surface at which the light is reflecting, you have different properties or attenuation which takes place. The goal is must derive a computer model for emission of light source scattered at the surface and representation at the camera. So you have got different objects being illuminated and reaching our eyes, and depending on that we have to generate a model. The desirable features are it should be concise, efficient to compute, and accurate, or as accurate as possible so that it looks real. If it is not accurate, it will not look real, and therefore your troubles are wasted. Direct or local illumination, emission of light source, scattering at surface, global illumination, shadows, reflection, inter-object reflections. That is, if you have multiple objects, it is possible that the light reflects from one object and reaches the other object and then reaches the camera. So these are effects which you need to consider in the global environment, or we call it the global illumination, or we can talk about direct or local illumination, where the light directly hits the surface and is directly processed and sent, or directly sent to the camera, so that you have a direct scattered image. Now let us assume a 3D world and we have a cylinder as an object. So we place a camera and we see here the camera looking at the cylindrical object. Now we position in the world coordinate the light source, and moment we position a light source, we see the object producing a shadow. So you have a ray tracing of light which emanates from the light source, hits the object, and using the reflection rules, you draw the normal at the point the light ray hits. The the reflected beam would be in the same will be in the opposite direction with the same angle. So these two angles being are same, right? And the reflected beam, if it enters the camera, is what we will observe as a direct illumination. Now, it is possible that a particular object may occlude the ray reaching the cylinder, and therefore instead of the ray you get a shadow, and the shadow is then reflected to the camera which you see. So, to generate or construct a model, let us assume an intensity pattern in 3 dimension. Assume the point which we which we are using to compute the illumination is at a location XYZ. So IL depends on the location of the point, which is XYZ. The light source is at an angle of theta phi in the spherical coordinates from the point of the light source, while lambda being the wavelength of emission. So here you have the light hitting the source at the point XYZ, and you have the normal. This makes an angle of theta phi in 3 dimension, and in ideally measured in irradiant energy for all situation. Too much storage and difficult in practice. So coming to the 3D model world transforms, we have seen that we have generated the objects in the model frame of reference, and then we have moved it into the world frame of reference. Model may be hierarchical. You may have multiple objects connecting to a single model. The lighting and shadow open in the world coordinate. The world to camera is a canonical transformation where I transform from the world axis, or an orthogonal transformation from a world axis to the camera axis. And that is where we have the projection, where we move from the camera to the image. A perspective projection is made so that it looks like a real scene where images are taken through a lens camera. Now, ray tracing, it may be very difficult to do ray tracing assuming that the light source equally illuminates, or rays from the light source are moving in all directions. So if we start by computing the rays from the light source which is moving in all direction, the computation is extremely large. Instead, we move in the opposite direction. We start by seeing a particular pixel on the screen which is illuminated by different objects. That is, we move from the camera to the object. So here is the arrow where we have moved from the camera to the object, and now drawing the normal to that object, we know that this is a reflected beam from the original beam, and then we can obviously, using the reflection laws, we can compute the reflected beam. And if we compute the reflected beam, and if there is a light source in that particular direction, we say that that particular light source is illuminating this point, and therefore the camera is looking at it. But it is possible that the light source may be at a different location than the reflected beam. In this case, this point of the graphics will have no illumination, or will not be directly illuminated by this object or by this light source. So here you see that we have cut the arrow, that is, this ray will not exist, or since it cannot find a light source. Forward rendering is how we compute this object. We take a position, we connect it from the object to the light source, which gives us the forward rendering. Now, ray tracing can be done using multiple light sources, point or more point and more complex light sources or extended light sources. We need to see reflections, refractions, shadows, and the software and hardware. We need to also do hidden surface removal, which we have learnt earlier. In ray tracing in advanced, we need to know anti-aliasing, blur reflection and refraction, glossy surface or matte finish surface will make a difference. There is something called the motion blur and depth of field and finite approaches. The big picture trace a lot of rays of light until they enter the camera. And we know most of them never do. So, therefore, we have seen the better way is to start from the camera and the light source, which the light rays or the ray tracing, which takes us to a particular light source, is retained while the others are discarded. So, lighting, there is something called local lighting and global lighting. We have seen this. Now, creating this model of lighting, we will say that the light is additive. Add more light and it adds to the result. Light accumulates from light directly, reflection of light from other objects, emissionness. Now let us start making the model for illumination. To begin with, we do not have any light source and the thing is dark. But in a dark room where we switch off all the light source, still we can see objects. This is because the sunlight or the starlight or some light in the neighboring room is leaking through some cracks in the wall or through some over gaps in the window and scattering in this room. And as it scatters in this room, it creates an illumination. Now, this illumination has no direction or the light source, or it cannot find the parent from where it it has obtained the light source. It is obtaining it from all over the room. That is, in other words, if we say objects not directly lit are typically still visible. Like ceiling in this room, and this is the result of indirect illumination from emitter bouncing off intermediate surfaces. It is too expensive to calculate in real time, so we use a hack called the ambient light source. Or we say that this light source is as if this amount of light exists from every object, and every object is illuminating the world and in the direction of the camera by some amount of light source, and we will call it the ambient light source. No spatial direct or directional characteristics illuminate all surface equally. The amount reflected depends on the surface properties. We continue with the ambient light source. For each sample of wavelength in our case, we are creating an image in red, green, and blue. In other scientific purposes, we may have specific images from very narrow filters. These are broadband filters, that is RGB. The ambient light reflected from the surface depends on the surface properties, that is K ambient, or we will call it Ka. Of course, the surface property is wavelength dependent, as we have seen in this piece of plant, where it reflects green's color because it has the property such that the green gets reflected, and therefore Ka is a wavelength dependent property, K ambient. The intensity ambient, which is again a wavelength dependent, generally it would be the sunlight, or if it is illuminated at night using artificial lights, so it will have a different property, and we will call this as Ia lambda of the ambient light source, constant for all points on all surfaces. Now, please note that this ambient intensity is uniform throughout the room, and there is no variation of it, because the light is so well homogenized that moment you have a direction to the illumination, that is no more an ambient source, but this is a term added over an ambient source. So here you have an ambient intensity which is generated. So basically, the intensity reflected is a combination of surface property K ambient and I ambient, which we write it as K lambda times Ia lambda. And of course, to keep it proper, we choose Ka between 0 and 1. So this is the ambient light source, a scene lit only with an ambient light. So what you see is that there is no shading. It's a flat sphere which looks more like a circular cutout from the image. It is uniformly colored with the same color, which is red. The light position is not important because we don't know from where the scattering is occurring. Viewer's position not important, from where are we viewing it. And thirdly, the surface angle not important because we don't know from which direction is this illuminating. So, but it's nevertheless it's illuminating. So we will attribute this as surface angles not important. Now, these are the basic three properties of ambient illumination. So, the ambient term represents the reflection of all indirect illumination. This is a total hack. So, here you see a graphically generated image. The region you see which is uniformly colored is basically the Ia term which is present, or the ambient term which is present. Of course, I have got regions like this region, this square, which is highly illuminated because it is a light source. So the light source will get more illuminated, or we have to add intensity to these light source, and because of this light source you see this shading effect which is occurring on the walls of this corridor, where you see that there is a dark mauve and a light mauve spots which are generated. The next term is the emissive light. Now, there are objects could be a light source. For instance, this is a light source or a lamp which provides a light of its own. And because of this light of its own, other objects like my face can be illuminated by it. So the surface itself produces light. What we have implemented so far is the I is equal to Ka lambda, that is, through an empirical way, we decide. What we have implemented so far is I is equal to Ka lambda. Of course, why I have used Ke because it is an intrinsic property of the illumination, and therefore it goes to the property of the object. So now the equation with the two terms is additive, and I have the emission term which is in front, and the second term is the homogeneous ambient illumination, which is Ka lambda times Ia lambda.
We begin here with an ambient light, and the scattering is uniform, and there is no shadows of any object, and I cannot say that there is a direction from where the light is illuminating these objects. The second term to these objects could be the term like this object that I am placing here. This object itself is an LED lamp, so it emits light by itself, and there is an emission term to this. So this is itself a light source which is generating some illumination. So this would be my second component to the model of illumination. If a particular object in my scene is a light source, we should show it accordingly as an illumined object, or should have sufficiently be bright to show it in this way. Next,
now we have two components of illumination. One component being the direct emission, and the second component being the ambient illumination. Please note the ambient illumination doesn't depend on the direction of light, nor does it depend on the direction and from where we are viewing. It is uniform in both. So the light source, the position of the light source or the position of the camera is not important. This can be produced for in the world coordinate and does not depend on the camera position at all or the position of the light source. We will end this lecture at this position, and we will see other effects of other two components, because up to now what we have is a flat illumination which has got these two components. We will take